We'll get started now. So the lecture this week, is it recorded? Yep, is sort of advanced segmentation and then supervised methods. And so we're combining sort of the lecture 5 and 6 together in this one from last year so that we have more time to cover some of the more interesting topics later. And if we go over, we'll just move the beginning of next lecture to next week. For the literature and useful references, it's fairly short for this. There's a couple of references here, and then the references from the last lecture that sort of extend into this one as well. And then we'll have a different set for the second part of it, just to keep things separated. So in terms of kind of the outline, sort of the motivation, as always, is sort of the first thing we'll go over. So why do we even have this material? Then some of these ideas with sort of thresholding, automated methods, hysteresis methods, so how we incorporate that. Then sort of a bit about sort of feature vectors, working with segmented images and beyond, and then we'll go into the supervised approaches in the second part of the lecture. So if we go kind of what did we cover previously in this class? You know, we had the image acquisition and representations from sort of the first lecture. We had the enhancement and noise reduction from the third lecture, and sort of understanding basic models and interpreting histograms a little bit from the last lecture. We also covered a bit of this idea of sort of ground truth and ROC curves, and choosing a threshold. So when you look at a data set, how you can kind of go about deciding if a certain threshold makes sense and applying thresholds to different dimensions within the data. We then covered at the end of last lecture how we can improve these segmentations. So sort of once you've done the segmentation, how you can post-process it in order to enhance the image a bit, filling holes, connecting objects, removing noise, and those were sort of the core concepts that we covered. And so now we kind of cover when are the techniques that we've done so far sort of insufficient. And so one of the first and most common cases that we have of this is sort of this inconsistent illumination. And so this is where, typically in like light field microscopy or even RGB images on your phone, that as the illumination changes, the brightness in your image changes, which means, if you pick a threshold, that might work for one image, but then it won't work for the next. And so how do we deal with this? And so sort of the example we have for this is this sort of simple cell colony image, where we have, a number of different images shown here, and all of them have different brightnesses as intensities. So we kind of assume this all comes from one microscope, but that the light in the background is flickering or slowly getting dimmer. And so all of the images have a slightly different brightness, which makes our challenge quite difficult to how do we pick a threshold when everything else is shifting. And so if we try to take a constant threshold like we covered in the previous lecture of sort of 0.6, we can apply it, and we see that on some images it works quite well. On some images it's way too everything above way too high, so we get way too much of the sort of noise in the background included in the images. At other images, it's then too low, and sort of there's very few where it's just right. And so if we were to look at some very simple metric from this, like volume fraction, so what percentage of the slide is covered with cells, even though it's the exact same image, here. So this is actually the same image with simulated different illumination. We have completely different values for the volume fraction. And so if you were trying to track something like the volume fraction with time, having a fixed threshold for this would give us very bad results, because every time you run the image and the illumination changes a little bit, your volume fraction changes significantly. That we see that the lowest value here is at 1.38%, and that the highest value is up here, but 24%. which means your metric isn't very sensitive. And so if you're trying to do analysis or compare different samples, it'd be very difficult to use a metric like this. Sort of another area where segmentation fails is in sort of like this caniculi, which if you're, we can zoom in, looking at sort of bone images, you have bone here, and then you have sort of these gaps inside of it. And so in this case, this is a blood vessel, and these are then little cells. And so these cells are blood vessels and cells are quite easy to see. You know, they're fairly small objects, and they're much darker than the bone that surrounds them. But the connections between these cells are quite difficult. So you can see this cell, for example, has this little sort of connection coming out of it, which is called a canicule. And this is then very hard to see. And so finding the cells is quite easy, but finding these small little substructures connecting them is a lot more difficult. And so, you know, the first task is easy. It's using a threshold and size criteria. We sort of know how big the cells are, and we can apply it. The second task is much more difficult because of these small channels that are about the same size as a pixel. Their density is almost sort of between bone and air, and it's very hard to make out. Sort of a third case where segmentation fails is this sort of example of sort of a brain cortex, where we see that the cortex is sort of barely visible to the human eye. You kind of have this red marked region, and that's the cortex. And it's, you know, doesn't have that much different texture, doesn't really have a different brightness, but, you know, tiny structures and sort of global positioning indicate where the cortex is located. And so trying to do sort of a simple threshold isn't really sufficient to finding these structures or labeling these structures well. And so we can see here that, you know, if we take this image of the cortex, we make a histogram for it, and we try applying a number of different thresholds, we don't really get something that overlaps with what we're looking for. So that the thresholds here sort of correspond to the different colors in this image. And, you know, like the white region and the light green region and the dark green region all fall into the cortex. And so none of those cutoff points would be a very good cutoff point for doing a segmentation with this image. And so kind of the first technique that we have for this is automated threshold selection. So if you use a tool like ImageJ or Fiji, and Python and KNIME have this built in as well. So KNIME actually uses the exact same threshold settings as Fiji. You have this sort of automated threshold selection. And so here, when you go to threshold, rather than seeing a point that you just set, which you can do with default, you have a number of these options down here. And so what all of these techniques are different ways of automatically setting the threshold based on the image or the histogram. And so what's quite nice about these is that these have been tested on large numbers of different images, and there's so many of them because there's many different kinds of problems that you're trying to solve. And so one of them probably works better for the problem you're trying to solve than other ones. And what's also quite nice is that they don't require any input. So by selecting one of these automated thresholds, it just applies its analysis in order to decide where you should put the threshold in the image. So just to back up. So does anyone have any idea how these methods would work? So if you were given an image and you had to come up with a technique to automatically pick the threshold, what would you do? Yeah?
You can look for a maxima automatically, then interpol them or make a mean value and then weigh the different histogram values according to a certain function, and then put the threshold in there.
Yeah. And which kind of images would that sort of work well for?
Or let's say that the difference, or I think it will just work if the histograms are already with shifted absolute values still like separate peaks with deciding which phase is which.
Yeah. So where most of these techniques work quite well is where you have sort of separated clear peaks. So whether you have sort of a peak and that you're trying to, or two peaks, making up the two groups in your images, and you're trying to find sort of a place in between them. And so that, you can find the maximum of those two peaks, and that you can sort of go between them and say, that would be the point that I would threshold at. So that technique specifically is called sort of intermodes. There's a number of other techniques, but a lot of them work on the same principle. So the sort of core principles we have with this are the first ones are sort of histogram-based methods. And so these are where you, just like we, visually inspect the histogram and sort of trying to decide a point to threshold at. You have an algorithm look at the histogram and apply some analysis to it in order to find the best point to apply the threshold. And so there's a number of different methods here, O2, isodata, intermodes. I think we'll go into them in a little bit more detail, but the basic idea is that they're able to find the two peaks, or they're able to find sort of the minimum and maximum entropy. I think isodata, what it does is it goes iteratively through the image. So it picks a threshold and it tries to see that sort of the two groups stay separated well, and they work that way. And so that's sort of the histogram-based method. The image-based methods is sort of the second type of thresholds that we have, where they look at the statistics of the images themselves. So when you apply a threshold, you can look at sort of like the entropy differences between the two groups and see if that threshold makes sense. And if it does, then you keep it. Otherwise, you can sort of change what your threshold would be to get the optimum of this. The final is kind of this results-based method. And so this one links back a little bit to what we were doing before, where we talked about sort of having these ROC curves, where you really focus on what are you trying to measure in these images, and then picking a threshold that gives you that value the best. And so in this case, you search for a threshold which sort of gives you the desired results in the final object. So at the ROC curves, we were trying to minimize false positives or false negatives. With result-based methods, we can be a bit more general. So we can try to say, we want a threshold where we find objects that are sized between 200 and 10,000 pixels. And so if the objects are smaller, we want to increase the threshold or decrease the threshold. And if the objects are bigger, we want to decrease the threshold. And so you have sort of a rule like this that you apply in order to pick the threshold out. So all of these methods sort of have their shortcomings, and all of them are sort of suited to different kinds of problems based on what you know about your image, what you know about sort of how your images are changing, and what makes the most sense to do. So if we take a very simple example of sort of this histogram method, we can take an image of a bone slice, and we can examine sort of the variations in calcification density in the image. We see that the histogram sort of has sort of two peaks, that we have this main peak here, which is sort of the bone, and then we have this peak over here, which is the air, and that we have sort of this fairly large region between them, and so it's not entirely obvious exactly which region we would pick. I can zoom that in. Boop. To do the threshold. So if you put it sort of all the way down here, you'd probably have some of the bone maybe labeled as, or some of the air labeled as bone, because you sort of made it too accepting of bone. And if you had it all the way up here, then you'd probably have some regions of the bone that you labeled as air that really weren't. And so you kind of have a tricky problem that, you can put it anywhere between here. If you take that sort of intermodes method, you would take these two peaks and just go exactly between them, and that would give you a reliable value for the threshold, but it wouldn't necessarily give you the best one. And so, intermodes is sort of taking the one between the two peaks. Otsu is search and minimize intra-class sort of variance. And so what Otsu does is you sort of change your threshold so that the variance within each group is sort of minimal, so that the groups are as similar to each other as possible. And ISO data, as I sort of mentioned, is this kind of iterative approach. So that the threshold you sort of guess by taking the max and the min and going right between. And then sort of while the threshold is still changing, you'd say the background is everything that's less than the threshold. The object or the foreground is everything that's greater. And the new threshold is sort of the average of the background plus the average of the foreground over 2. And then you sort of update it, and then you continue until it stops changing. So what's quite nice is that there are lots of tools that let you try all thresholds. And so in Fiji, Scikit Image, KNIME, you have very easy interfaces to load in an image, and even a function here called sort of try all thresholds, where it takes it, it shows you the original image, and then it shows you what each threshold on your image looks like. And so we don't cover all of these techniques in the class, but that you could run this on a number of images and try to figure out which one of these was focusing on the right features in your image. And so we see that, the Lee one seems to, get sort of holes, but not these darkest ones. So if we wanted to get just cells, but not blood vessels, it looks like that would probably be the best technique to use because it kind of ignores the blood vessel fairly well. Minimum also seems to give that kind of result. Otsu gives a pretty good job of giving us blood vessels and cells, but with lots of background noise. And then we see Yen and Triangle focus on entirely the wrong thing in the image. So there might be cases where we're interested in sort of these borders around the cells that are really bright. But of course, these methods just look at the image and try to figure out what could be interesting inside it. And it doesn't know that we're interested in the cells, or if we're interested in the rings around the cells, or if we're interested in the blood vessels. It just runs its automated approach. And so based on what we're looking for, we can sort of pick which method fits well, or even combine the methods together in order to get sort of a nice result. But often, you can know everything there is to know about ISO data and still not be sure it's applicable to your problem. It's not really something you can solve with a model. It's something you kind of have to try on a large amount of data and see if it works well. And so for a lot of these tools, it's just about getting a feeling for what they show and when and how they perform in different kinds of cases. So sort of the test that Anders Kestner said in the 3rd lecture, this sort of smoke test of, if you give it a really, the worst image you can imagine, some normal images, and then the best images you can imagine, you want it to work well in all of those cases, or you want to choose the technique that has sort of the best performance in all of those cases. And that what you'll find is that with a lot of these automated techniques, in the really horrible images, they end up giving results that are very bad and sometimes sort of counterproductive. And so this is kind of the pitfalls section. And so there's a number of different pitfalls that come with this. For sort of histogram methods, sort of the biggest issue here is that they're very sensitive to the distribution of your pixels. And so, if you have images where you have equal amounts of both phases, then it works quite well. But if the amount of each phase changes significantly, the image the approach will sort of shift to whatever you have sort of more of. And so, in this case, if you had if we go back up, if you had a bone slice that didn't have any holes or bone or blood vessels in it, and you applied some of these methods, they would find a segmentation. They would pick a threshold value in order to find things, but they wouldn't find the things that you were looking for. And so if you're not confident that all of your images will have a similar amount of both things present in them, then it's quite important that you sort of use these methods with care, or at least check your results after using them. Similarly with sort of microscope images, we've seen a number of applications where you're trying to do kind of real-time microscopy, where you're like following cells on a slide, and these methods work really, really well, and then the cell sort of leaves the field of view and you have no cells visible anymore. And then these will find dust to segment because they'll always try to find something to split in the image. And then you'll end up having dust that you track for half of your experiment because there's nothing else to track. And if you don't manually check it, you might end up coming up with results that are based on how the dust moves, not based on how cells move. So for the histogram method, this, knowing that these things are similar and doing sort of these smoke tests of what do the variation in images look like. Image-based can be quite sensitive to noise and large noise sort of content. And so if you have noise levels in your image that are changing, if your illumination goes down, obviously your image is darker. But what also usually happens is that the noise levels in your image compared to the signal that you're looking at go up. And so if your noise levels are changing drastically, some of these image-based methods can give you really bad results. And then results-based are sort of inherently biased by whatever expectations you have. And so if you pre-program in your model that you want to have cells that are around 200 to 1,000 pixels in size, and then you measure the size of the objects you find, it's quite clear that you'll get objects that are between 200 and 1,000 because that's exactly what you segmented in your image. And so it sort of takes away some of the meaning of trying to then measure size in your image because you chose your threshold based on size. And now you're measuring you would of course find what you're looking for. And so with those, you sort of have to be careful about what you do afterwards because you're using that to decide what your sort of inputs are. And so in terms of kind of the realistic approaches with dealing with these shortcomings, so you can obviously go through the models, you can run it with millions and millions of images, but often this isn't easy or very time efficient to do. Sort of one of the easiest approaches, if you're comfortable with these techniques, is this sort of model-based. And so if you can try to simulate everything, including noise, then you can sort of apply these techniques and see how they work as you add more noise to the image, as you change your illumination, as you sort of change the distribution. But if you can simulate your images quite well, and you'll see from lecture 3, we simulated noise in a lot of the experiments. So we took perfect images, added noise, in order to check how well our filters worked. And you can do the same thing with these threshold techniques, that you take something, you add noise, you add illumination differences, and then you try different techniques to see which ones give you the best result. Sort of the sample-based, you can apply these methods to each sample and keep track of which thresholds were used, and then go back and apply each threshold to each sample to kind of get an idea of how much your threshold changes and what results, how reliable your kind of results are. And so by doing it with a large number of samples, you'll get a better feeling for what that sort of range is, and that you can try applying different thresholds to different images and seeing how much it changes your final output. And so if it changes it significantly, you potentially want to tweak your method a bit. And if it doesn't change very much, then you're in a fairly stable area. And then the last is kind of this worst case scenario. So this is really then the smoke test, where you try to come up with sort of what are the worst images you have, and how can you verify that you get sort of reasonable results out, or at the very least that you're able to identify that this is a really bad image and sort of ignore it from your future evaluation. So if a lot of the really bad images, you're not going to be able to get something meaningful out of it. There's just too much noise. There's nothing you can do with it. But you can at least try to find out a way to identify it so that you can ignore it from your analysis. So kind of the next technique we'll go over is this idea of sort of hysteresis thresholding. And this is where sort of single thresholds don't work. And so this is a fairly easy to use technique where you kind of have larger structures that are clearly defined and smaller structures that are kind of difficult to differentiate. And so here we have this image again with the bone, where we see that there's this sort of very clear cell structure, fairly clear bone structure, but then there's these sort of holes and these smaller substructures that we're trying to identify. And we sort of have this problem that, you could identify the gray fairly accurately, where you see the, gray cells here. The yellow as sort of those in between, where, it's potentially the structures connecting the cells together, but then a lot of sort of noise and possibly artifacts. And then the green, which is sort of clearly bone structure. And so what you end up with is this kind of Goldilocks situation where you have, one threshold that's way too low and one threshold that's too high. But, finding one that's sort of in between that works well isn't very easy. And so, here the threshold of 70 gets the cells quite accurately, but the threshold of 110 gets the cells but gets a lot of other junk. And so it's hard for us to get everything we want without getting a lot of sort of noise and junk as well. And so this is where we try to get sort of a happy medium between them, where we use this hysteresis thresholding to combine the two images together. And so we basically take the more strict one as the initial starting point, so the things that we're very confident that they're cells. So when we go here, we can say everything in this, we're fairly confident it's a cell, and we'll use that as a starting point. Then we remove the objects, which are sort of not smells, which are too small or disconnected from everything else. And then we can take a second threshold at sort of the higher value, and then we can combine those two images together by only keeping pixels, which are connected, and this is sort of by using this neighborhood that we mentioned before, to air voxels, and ignore the other ones. And so this kind of goes back to the noise structures here are only meaningful if they're sort of connected already to one of these cells. And if they're not connected, then it's not meaningful. And so that we have sort of the strict threshold initially. We clean it up by performing an opening operation. We then perform this much looser threshold. We then sort of have both of these thresholds together, where we have sort of green for the less restrictive and red for the restrictive. And then we can do this sort of connected threshold, where we keep everything in the green that's directly touching a cell. And so that this gives us the ability to kind of get both of those benefits in the system so that we can start looking at connected sort of cell structures much better. We have sort of more complicated images as well. So if you look at sort of color images or MRI or sort of hyperspectral images like you get when you're doing spectral imaging, or sort of coherent diffraction techniques where they produce sort of a 2 or 3D pattern at each point. You have sort of more complicated approaches, but you still have the same kind of techniques that you can apply. So that if you look at an approach like ISO data, all of the steps that were involved in ISO data you could easily apply to a vector, a tensor, a whole image, that basically it requires you to take the maximum, the minimum, and divide by 2. And so anything that you can apply that technique to, you can also apply, you can also sort of run quite easily with these techniques. And so just because the unit you're dealing with is no longer sort of an intensity value, it's now an RGB value, doesn't mean you can't apply the same sort of techniques to those. And so this is sort of where we have this idea of feature vectors, where we try to have sort of a pairing between spatial information, position, and some other kind of information, the value. And so this was sort of our original definition of an image, where we try to link the spatial features with the values that we're trying to have. And we know that we have sort of many different formats for this. And so this is where we start to look at, we have this scan from a book where it's sort of unevenly illuminated. And so for anyone who's taken a picture with their smartphone or tried to scan a picture or document with their smartphone, this is a quite frequent problem that you have. And, the techniques that we've covered so far wouldn't give you a threshold value that worked well for this image because there isn't really a single threshold value that works well. You have a problem that your illumination isn't constant over the image, and you sort of need to correct for that first. And so what we have is this sort of, same description that we covered in sort of the first lecture, where you have sort of an X position, a Y position, an intensity, and then this sort of label, is it foreground or is it text? And so we now have our whole image kind of represented like that. And that rather than saying, is this an image with sort of a, intensity matrix, what we have is a sort of feature vector. And so our feature vector is X at 153, Y at 99, intensity is 174. And so really what we're trying to do are find which combinations of these features are text and which ones are not. And so this makes the problem a little bit easier, that, if we look at the intensity distribution, we kind of see that, text tends to have sort of the higher values, but there's a huge amount of overlap between these two groups. So trying to come up with a single threshold point here would be very difficult, because if you put it here, you'd have a lot of non-text that you sort of classified as text and a lot of text that you classified as non-text. And so because these two overlap so much, it makes it very tricky to do. And, if we try to make an ROC curve using sort of just the intensity, we get a reasonable result. So we get sort of a 0.82. But obviously for text recognition, a 0.82 isn't nearly high enough. If you're misclassifying a large number of pixels, it's going to be very difficult for you to do text recognition well. And so this is where we can kind of add additional information, where we start to see the image much more as a feature vector than just an intensity value. And so what we can do here is that we can add sort of, this edge component. And so rather than just having the image by itself, we can add this sort of difference of Gaussians filter, where it's just, two Gaussian filters applied and the difference between them. And so here we have, 0.5 and 10, and then we end up with an image like this. And so this is sort of the raw image that we put in, and this is now the Gaussian filter. And so we now have sort of 4 features in our feature vector. We can now see that edge separates these a little bit better than we had before, so the groups are much easier to work with, but they're still overlapping quite a bit. And so by just doing the Gaussian filter, we have, by combining the two, we now have sort of a much better performance. So we go from 0.82 to 0.9 by taking the intensity and adding the edge values to it, so that we improve our model already quite a bit by just incorporating these two different values. And that we can now sort of go even further. And so one of the most useful techniques that you'll cover in this class is called sort of k-means clustering. Has anyone heard of k-means clustering before? Does anyone feel confident enough to explain it, or at least explain their understanding of it? Nope.
So you basically look for a pixel that are near to a k value, more or less.
For k-means clustering?
Yeah.
Sort of. So with the k-means clustering, so it's actually used, it's a technique that's not limited to images at all. So it's a technique that's used in all sorts of different fields. And so most of the people using it actually are not doing image processing. So the image processing applications sort of have something more to do with the pixels. The most uses for it are looking at sort of tabular data or user account data. And so, Google, Facebook, Twitter regularly use these kind of approaches to classify customers, advertisements, queries. And sort of what it's a really nice technique for is that it allows you to cluster multi-dimensional data into groups.
But is it like the same as a neighborhood?
No. So what we did in the second lecture,
Exactly.
that's k nearest neighbors.
Exactly.
Yeah. So k means clustering and k nearest neighbors, even though they sound similar,
Right.
have nothing to do with one another. The only, I guess, similarity between them is that they both have a k.
That's it.
Well, so that, with the k nearest neighbors, you can say, k equals 5. And that's then you look at the 5 nearest neighbors
Exactly.
to evaluate sort of to make a prediction, or the 1 nearest neighbor. And with k means clustering, k is the number of clusters. So the k, you're just specifying, do you want to find 2 clusters, 5 clusters, 100 clusters when you run this model? And so there probably are more techniques that also have this k in them. I don't think of them right now. But basically, it just means that you sort of predefine this k when you make it. And so the k nearest neighbors is sort of a model that we use for prediction. And this k means clustering is sort of a model that we have for clustering data together. So we're actually not trying to make a prediction here specifically. We're trying to take sort of a large set of data and group it in a natural way.
It's unclear. Sorry.
Yeah.
Because, when you do like a neighborhood, you just pick up the distance between object, basically, right? And here the clustering is actually, what is it? A cluster here is like, again, a group of objects that are classified by distance between them, or
Yeah. So it's a similar idea that you still have sort of this distance metric.
okay,
So that basically, if we look at kind of the inputs with what we take, so you take a bunch of feature vectors that you put in. So a bunch of like pixels from your image,
yeah,
or if you're Google, it could be a bunch of search queries that you've been given.
yeah,
You then have a distance metric, and so that basically says for any 2 of these feature vectors or 2 inputs, how do you measure the distance between them? So for a pixel, this is quite straightforward. This would just be the pixel intensity difference, or the magnitude of the pixel intensity difference. But for a search query, this would be quite difficult to come up with. If someone searched for, I like dogs, and someone else searches for, variations in canine behavior, how would you come up with a distance metric that would say that they're very similar to one another? And so both the k nearest neighbors and k means have this distance metric idea. So you need some way of being able to compare 2 samples and measure the distance between them.
okay,
So in all our cases, this will be easy because we're just dealing with numbers, and so it'll be Euclidean distance. But for other things, like when you're dealing with search queries, or Facebook profiles or LinkedIn profiles where you're trying to find people who are similar to one another, it becomes a lot more difficult because making a feature vector and a distance metric for people isn't really obvious.
so can it be this useful for object or pattern, basically recognition, something like that?
Yeah, so you can use it for that. So what it's really useful for is when you have a ton of data and you don't really know how it's organized. So that sort of, if you imagine, someone gives you 1,000 books,
Yeah,
that you would use something like k-means clustering to be like, well, what are even the categories of books that I have? Where you don't necessarily know what kind of books you have, but you want to sort them into groups. And so that's kind of what the output from this model is. It gives you a classification of each feature vector into a group. So we'll have some much better examples of this that are hopefully a bit more concrete in the second part, but that we sort of have, an example distance metric would be sort of this Euclidean distance. The group count n equals 2, so this is kind of what that k is referring to, but usually it's called n just to make it more confusing. But that basically what we have is this sort of fairly simple example where we have these points, and we'll look at these points again. And if someone gave you this plot of sort of x and y points and told you to divide it into 2 groups, even without knowing what the x and the y axis means, you could sort of divide it into 2 groups, right? I mean, you could just say I would draw a line here, and everything in the upper left corner would be in group 1, and everything in the bottom right corner would be group 2. And the x-axis could be hours of the day, and the y-axis could be, number of frogs that are outside or something. But it doesn't really matter. You can just take the data without knowing anything about it and apply this kind of clustering to it. And so that's exactly what we do with k-means, that we're able to take these data. We say we're looking for 2 clusters. We sort of give it an initial random state, just so that we get the same result every time we run it. And what it gives us is it says, here's one cluster and here's the second. And so it's able to take this data and just divide it into 2 groups, which is actually what we were trying to do with the automatic thresholding techniques as well. So you just gave it a bunch of pixels and said divide these into 2 groups, and then I'll try to figure out which group refers to the foreground and which one's the background. And so what's quite nice about this algorithm is that you don't really need to know anything about the groups, and it will always find, or almost always find, what you're looking for. And so what you do is that you sort of randomly create center points in the space that you have. And so usually this works by just randomly sampling points in your space. And so you'll take one point and say this is in group 1, and another point and say this is in group 2. And then you go through all your data and assign the group to the closest center. And so once you've labeled 2 centers, you can assign the group by whichever center it happens to be closest to. You can then recalculate the centers from the mean point of each group, now that you've assigned a group to each point, and that you can go back to 2 until the group stops changing. And so you kind of run this iteratively, and it will divide your data into 2 groups quite nicely, or n groups quite nicely. And so if we think about kind of what sort of vector spaces do we have, sometimes they sort of represent physical locations. If you're trying to classify Swiss people into cities, you could take the latitude and longitude of each person and, search for 30 groups, and you'd probably end up with groups that overlapped with cities pretty well. They can include intensity or color. And so, k-means can be a very good thresholding technique when you give it sort of the intensity and the color as part of the image. They can also include sort of orientation, shape, or in sort of extreme cases, full spectra. And the sort of key point with this is that this technique is really dumb. So it doesn't have any common sense. It doesn't say, it looks like you've tried to find too many groups. It will sort of always give you a result no matter what you look for. And so if you're looking for n groups, it will always find it whether or not they really make any sense. And so we can take this data set, for example, and we can look for 4 groups where you see that, maybe these 2 are separate. Maybe there's 3 groups. There's definitely 2 groups in this data. Maybe there's 3, but there's probably not 4. And yet it's still able to quite reliably classify all the points into 4 groups. But it's sort of up to us to have the judgment and subject matter expertise to know if these groups that it's clustered actually make sense, or if it's just sort of finely splitting or subdividing things that are part of the same group. So we can also apply it to this sort of Cortex image, where we take it and we include sort of this feature vector, and we just have k-means try to divide it up into different regions. And so what we can have here is we can put the data in. So we put in the x, the y, the intensity, and we have it try to segment it into 4 groups. And so our first result sort of looks like this. So can anyone think of what went wrong?
They're not well grouped, right?
Well, I mean, for the model, it thinks they're well grouped, right? It's just done upper left, right.
I think it also took the background, right? The black part.
Yeah.
So then you're not, because the black is so much different, from the tissue.
Yeah.
It's so much different from the black that actually from the black influence makes the group. You know what I mean?
Yeah. Yeah. So that's.
So the differences in the tissues are too small to be detected.
Yeah. So that's one of the one of the things that can happen is when you have sort of, if you're looking for small differences inside tissue and you have huge differences in your image, that sort of k-means will very easily focus on the big difference between your images, or these automated approaches will focus on the big difference rather than the sort of small subjects here. But with this, sort of just thinking about the problem we have, where we put in the x position, the y position, and the intensity into our k-means, and our output doesn't resemble the image at all, right? It just sort of drew a cross through this. Yeah? Exactly. So because the position values are 118 and 158, and the intensity values are 2.6 and 18, when we have our distance metric, it basically does a Euclidean distance, and it says intensity is the same as x and y are much, much bigger than intensity. And so what we've had it do is effectively just draw this cross, because it grouped the points based on points that were in sort of the same position. So it was just using the x and y position. It was kind of ignoring the intensity completely. And so how would you fix this? Or how could you fix this? Yeah, so you can either normalize, or you can sort of rescale and weight your distance function so that you account for intensity more than the position. And so this is where we can sort of scale the intensity, the x and y positions, by 10. And sort of now we run the clustering, and we sort of get a much, at least more image-based clustering of what we were looking for. So it's still quite far away from the kind of hope of getting the cortex perfectly segmented, but it's starting to look at least more like the image we put in, and not just like the data that we, the x and y coordinates where it's completely ignoring the image. And so we can try to sort of tweak it even more, where we sort of look for 5 groups, and we actually see that, if we play with the parameters enough and run it enough, we end up with a situation where it's able to get a reasonable part of the cortex fairly reliably, where it's kind of able to group the image by position and intensity fairly well. So it's able to take kind of both of those factors together in order to break the image up into pieces. And so what would be the problem with using this technique if you wanted to, take 1,000 images of cortexes and automatically identify them? Yeah, so if the image is tilted, then and applied this directly, then it wouldn't really take account for the tilt, and so you'd kind of end up using the old position information and trying to kind of overlay that. Any other issues that you might come up with? If you tried to run k-means again, what problems might happen? So this, this is all group 1. If we ran k-means again, would this still be group 1? No. So each time we run k-means, it sort of has a random initialization. And so when it comes up with groups, the differences between the groups are quite useful and helpful, but the group identities themselves are quite meaningless. And so this would tell us, if we ran this again, we'd probably get a similar image, but this could now be group 4, and this could be group 2, and this could be group 1, and every time you run it, those change. And so if you try to sort of apply this to, I'll use this to segment my image, you kind of have to account for the fact that if you rerun it, you'll also have sort of new groups to identify. So you'll need to come up with a way to sort of classify what you get out of it, because the labels themselves aren't very useful. So this now feeds quite well. I don't know why that image doesn't show up. Into this idea of sort of super pixels. For whatever reason, their website isn't working very well, but it's was actually quite a bit of the development work was done with a group at EPFL, and this is sort of taking k-means and making it much more useful for images, so that rather than kind of having to deal with all of this, having the image as a feature vector and including all these different weights, that they have one function that runs really efficiently for running k-means on images in a reasonable way. And so kind of why superpixels are useful is that kind of for the images we had before and a number of similar problems, that it's kind of k-means applied to images. And so it lets us sort of group the images together into similar regions and regions that are sort of have similar intensity values and have similar positions. And so if we start with an example of kind of a rock with multiple phases, like this, we can start to apply sort of a threshold to it where we apply these, different thresholds at different points. And we end up with sort of these values, but that we see that there's kind of this arbitrary split here because those values get a little bit darker towards the edge. And this has sort of the inside as sort of a lighter intensity than the outside, and kind of these other problems that make it very difficult to just use a threshold by itself. And with superpixels, what we do is we kind of run a k-means on the image, and we end up breaking the image up into a bunch of different chunks, where each chunk is kind of fairly similar to itself. So it all has sort of a similar intensity, but like a small dot tends not to affect the chunk too much. And so now we sort of have the structure of our objects kind of grouped together, and we can go through and decide for each one of these superpixels what it's likely to belong to and how to kind of classify it. And so we make our problem quite a bit easier because instead of having millions of pixels, you just have hundreds of superpixels that you can go through. You can look at the patterns inside of them. You can look at the average intensity. You can look at the shape and decide if it makes sense to keep it or not as part of your object. And so this sort of approach allows you to run k-means to break up your image quite well so that you have a much better starting point for the sort of future analysis you do. And so this will be quite relevant for when we start to do kind of the texture analysis and shape analysis, that a lot of times this is sort of the initial step you take to break up your image, and then you can just analyze the superpixels you get out rather than trying to analyze each pixel by itself. Yeah?
How sensitive is this method to, let's say, find structures that are just slightly above the resolution level?
So for those kinds of structures, superpixels tend to work fairly poorly. So if you were trying to segment like pixel level sized things, superpixels probably wouldn't be the right approach to use. Because if you're trying to get an object that's just a single pixel, then you'll end up with a situation where kind of a single pixel, yeah. And if your superpixels are the size of single pixels, you haven't really helped yourself very much by running superpixels. But as soon as your objects get a little bit larger in size, then these help you kind of group them together without really losing resolution. Yeah?
What if the picture is large blurry? Like if I look at very tiny particles, it's just like the resolution natively isn't that high.
Yeah.
So I get like 3/4 of like round my object.
Yeah.
But you can still like is it still able to like form cluster or is it then rather difficult?
It's probably difficult. So it depends a lot on the case. I mean, when it's really, really small, there's not much you can do with it at all. And as they get bigger, it becomes easier and easier to use superpixels to look at it. And that a lot of times, even if you had structures that were just the size of objects, if you were interested in white dots, inside of clay, the superpixel obviously wouldn't get you that white dot, but it would help you figure out where all the clay is located. And then you could analyze that clay and look, are there any white dots inside it? And that otherwise, if you just did like a thresholding, you might end up with this white dot in one group and this clay in another group, and it would be then much harder to figure out what's inside of other things. Yeah?
So you made a very good question. The previous method that became
Yeah.
clustering is not able then to distinguish from a very high background noise. Then, if you have an object with a very blurred
Yeah.
edge, and very high background noise, it will have hard time to distinguish the object.
Yeah,
Easily.
it will. Yeah.
Okay.
And this method will probably also struggle, but this method has sort of a slightly better way of kind of grouping things together. But if you have a lot of noise, neither k-means nor superpixels are going to help you get rid of that noise. This is only once you've sort of processed your images and you want to sort of extract the structure and information from it. But if it's, a really blurry edge, this won't make it less blurry. This will also struggle with a really blurry edge. Cool. So that now, we can, in this example, we can replace each one with the mean value so that you sort of get a much smoother version of your image where you still have sort of your edges preserved, but you don't have all the sort of noise and artifacts inside it. And that, we can start sort of processing and thresholding based on that. And so, we can do a superpixel segmentation and then group that into different categories. I think the labels for this are wrong. But this is the superpixel segmentation and this is the standard segmentation. And so we see the standard segmentation kind of has all of these kind of mixed values where there's, holes inside of it. There's single pixels that are labeled certain ways, and that the superpixel gives us a much smoother representation for our image. So that when we're looking for the areas that are generally clay or the areas that are generally sort of this air between them, this makes that a lot easier. We'll leave that out at the moment. That's not a super helpful slide, but that, I guess, leads into a little bit of what we'll cover in the next part of the lecture. So are there any questions on that? Yeah.
It's about the initial part that I did not ask at the when you showed the cases with different brightness,
yeah.
If we perform like an histogram equalization or something like that, would it help?
Yeah.
The threshold selection?
Yeah. So that's another approach you can have, is you can do sort of a histogram equalization as part of your image enhancement step, and then try just applying the same threshold. So it's very similar to applying, ISO data after without equalizing is probably similar to equalizing and then just performing a constant threshold. So that's one of the steps that you can apply very well to do that equalization, and then do your analysis on it.
The next question is also related to the sequence of steps. So because at some point you mentioned the noise in the image, so we would not initially perform the denoising and afterwards the threshold selection. So when do we have images to apply a threshold that have noise?
Yeah.
Because I assume that we would always remove the noise as the first step.
Yeah. So that's always the first step, is to try to remove the noise, but a lot of times you can't remove all of it. Or the more you try to remove noise, the more signal you remove in your image. And so in most cases, even after you've done denoising, you still have a lot of noise left over. And so the challenge is when you still have noise and you still have other artifacts, how do you deal with them in the segmentation process? But obviously, if you can get rid of them completely in your filtering, then your segmentation is easy or much easier. And so, if you can, you should try to get rid of noise as early as possible. But a lot of times you can't get rid of all of it, or you want to, particularly if you're looking at really small, blurry structures, if you filter everything very strongly to get rid of all the noise, then you've also lost all your small, blurry structures. So, Anything else? Yeah. Yeah, so the algorithm for it's fairly complicated. So I think there's a reference at the beginning that shows you how the details of that work. But that basically, for our purposes and how we'll use it, you kind of have this n segments, which says approximately how many superpixels you want to look for. The compactness, and then the sigma. And the sigma is sort of how strongly it should sort of filter the image data before it uses it as part of the feature vector. And so the compactness, if it's really high, will, I mean, we can actually do it right here. It should be quite easy. So here's that initial image. And then here we can run this again. And so we have the superpixels. And so if we take the number of segments and turn it into 500, we see we now get much, much, much smaller superpixels. And if we turn it into 50, we now get much larger ones. And that if you take compactness and you change it from 0.1 to 10, you now end up with perfectly square blocks, so it doesn't look at the image at all. And if you change it to 1e-4, then you end up with really, really crazy zigzagged structures that really just follow the images and don't try that hard to be connected at all. And so all of these values do have some sort of physical meaning, but it's easy, but it's quite complicated to go into kind of all the details for them. And so for the most practical purposes, you'll just be changing these parameters and seeing how the results change based on them. Okay, so we'll take a short break. And